our first speaker, Prof. Stacey from Wits University, but also with connections with SRK.
Morning. Morning. I hope this is perhaps a little bit different. I hope you don't think I'm being stupid. I'm going to be asking questions. So that's the title. And what information do geotechnical engineers need in mining? And if one looks at it, obviously we need information on geology, structural geology. For rock engineers, we definitely need rock mass strengths and deformation properties. We also need to know what the in-situ stresses are. Also, what affects conditions is groundwater, and if there's any seismicity, what are blasting effects, and so on. So those are parameters that affect what we do. Just a little bit of background as far as geophysics is concerned. A long time ago now, when numerical modeling was in its very early days, I did some finite element analyses, and at that time we needed to know what the modulus was of the rock mass to be able to do those analyses. And I came across a publication that showed a linear relationship between the static modulus and the frequency of S waves. So I thought, oh, fantastic. And then I had the opportunity of doing a number of laboratory tests using ultrasonic P and S waves, investigating the effect of frequency, wavelength, velocities, so on, and the effect of jointing, clay on jointing, water on jointing, and confining stress. So I did a whole lot of laboratory tests to try and really prove this graph. And the results that I got were that, showing the results between the static modulus and the S-wave frequency. You can see it's sort of a straight line, but a lot of scatter. So really not very convincing, which was rather disappointing. But it showed that geophysics is going to show the effect of joints, of confining stress, of orientations, and so on. So it was positive regarding the potentially valuable information that geophysical investigations can provide. So I'm very positive about geophysics and its applications. So common geotechnical problems are exploration boreholes are limited in mining because they're often mineral resource focused. Whereas if we want to know what is important as far as the rock engineering is concerned, we need to know information about the waste rock because that's what's left behind. So that's the boundaries of excavations are all in the waste rock. Borehole core, as we heard yesterday, is like a straw, provides some information, but really very limited. And particularly it can depend on the orientation of the boreholes as well. So there's limited detail on rock mechanics, on rock mass conditions and properties. And unless we've measured the in-situ stresses, we actually don't know what they are. And ore bodies may be at great depth, and therefore any boreholes are going to be very expensive. And this applies nowadays to civil engineering as well, where civil engineering tunnels are often being driven through mountain ranges with covers of 2 to 3 kilometers, that sort of thing. So any investigation becomes very difficult. So what is commonly done in rock engineering? Well, obviously, rock material laboratory strength and deformation tests, that's standard. Structural interpretation is done, but often one can't see where the structures are when it's deep in the rock mass. So if we do it from borehole core logging and mapping of exposures, it's often a long way away from where we actually need the information. And then commonly we use rock mass classification to put a number to the quality of the rock mass. Now that's potentially very useful. Now this is an example, more recent example of a type of rock mass classification called the Geological Strength Index. And it was developed by Everett Hook, very, very famous and very excellent rock engineer. And it's very simple in that you look at a picture which gives you the structure of the rock mass and then the quality of the rock as far as weathering and so on is concerned, and the joints, and you can put a number to that. Okay, so it's very simple. One of the other developers of a rock mass classification system, Nick Barton, who developed the Q system, described this as pictures for children. Okay. Well, then we use this information to calculate a rock mass strength and a rock mass modulus. So once we've got a number, we can then do these calculations. And then that gets put into computer programs, and we can do computer analyses of stability using that input data. And often, if we don't have the in-situ stresses measured, we've got to guess those. So we estimate the in-situ stresses. And we do very fancy numerical modeling analyses of the conditions. I took these from a publication, a fairly recent publication, which just shows you the equations that can be used and are built into the computer programs. So the modulus, you can see there, is a function of the GSI with a very fancy formula. And there's a D factor as well, which is a fudge factor. And I'll show you a picture of that as well. And then the strength. You've got the sigma 1, that's the strength of the rock mass, as a function of sigma 3 and other factors, which are factors of the GSI. So there's fancy equations there that are allowing you to calculate the modulus and the strength. You'll notice that in the strength calculation, it's a function of sigma 3, but not a function of sigma 2. But we always have 3 principal stresses. So it's ignoring the one principal stress. This is the fudge factor, the D factor, which varies between 0 and 1. And it just takes into account, factors like blasting and what the quality of the material on the joints is and so on. So you look at the pictures and you say, oh, that's right, we'll put in a fudge factor of 0.5. So those equations then are built into computer programs, and they allow any user to carry out, and I put in inverted commas, sophisticated analyses of the stability of the rock mass, whether or not they understand the limitations of the process. And I've got an example of from students at the university, the undergraduate students who might do calculations and so on. And I've had students who come up with very confidently a stress of about 3,500 megapascals. And they don't think that's strange at all. That's what came out of the computer. Okay, and this is the problem, is that these things allow inexperienced people to do very sophisticated analyses with these computer programs. So with this approach, can we expect reliable predictions of stability? Obviously not. Now, this is an example that I've been involved with. This is an open stoping operation in a gold mine. Now, in Canada, techniques were developed for evaluating the stability of open stopes using a rock mass classification approach. And it's been very successful in the mines in Canada. It was applied here in a gold mine using open stoping methods, its target mine. And look what happened. didn't work. So it caused problems with the equipment, and all that material coming down, in fact, is waste material. So you have a lot of dilution as well. So in fact, my student developed a technique to design those things, and it worked extremely well. And as soon as that was implemented, it actually resulted in hundreds of millions of value for that mining operation, because it stopped the damage to the equipment, it stopped the dilution, and it also stopped wastage of time. Second example, this is a rock mass, and you can see that it's a bedded rock mass. There's a few cross-bedding. You can see one joint here in the front, and right up, I think on the right-hand side at the top, you can see another joint. So it's you might say, it's obviously anisotropic, but it's a fairly massive thing. So if we look at a rock mass classification, and this is getting a rock mass rating rather than a Q thing, but from the same system, we can see that it would fall into the intact or massive category. And you can see there, it's obviously in that category there. And the second description is slightly, rough, slightly weathered. So it's probably in that area, which gives you about a value of about 85. Okay, and if we look at an estimate of the support required based on rock mass classification again, this is for a 14-meter span excavation at a depth of 160 meters. So not high stresses or anything like that. So that's going to be, that's going to be up there somewhere, 14 meters, okay? And 85 is going to be out there somewhere. So it will fall in the no support required category, okay? Now, they did put in some support, but what happened? Well, that happened, the first thing. That was about 170 tons that fell down. But prior to that, there'd been a small failure, and there'd been quite a lot of popping. So minor seismicity actually occurred. You wouldn't expect that necessarily at a depth of 160 meters in sandstone. Okay? They didn't do anything. They just cleared this away and carried on. But you can see there was support put in there. And then what happened? Well, that was the next one. That was about a 70-ton failure. And you can see it broke rock bolts, and it's obviously failed through intact rock. After that, this was stopped, and they had to put in more support. And they actually put in about 4 times as much support as they planned originally. And the designers were sued by the owner, and it went to mediation. I don't know what the ultimate cost was because it's confidential. But the owner came out of the mediation smiling all over his face. So in round numbers, he got paid out 100 million Australian dollars, which is R1 billion in round numbers. So that's the cost of the mistake. Okay. So the approach is applicable perhaps for an isotropic rock mass, but rock masses are really completely isotropic. And that's isotropic in terms of in situ stresses as well as structures. It's very useful, this rock mass classification is very useful for non-geotechs. So if you imagine a mine manager or a director of a mining company who happens to be an accountant, he could understand this and he could go and look at rock mass and get a number. And I think that's very valuable. Also, reasonably unqualified technicians can put numbers to the rock mass as well. And that's again also very useful, but it shouldn't be abused. So why should an E and a strength for the rock mass be related to a rock mass classification number? And the question, what is a rock mass E? What about Poisson's ratio? I mean, that's very important in analyses, but I have never heard of any measurement of Poisson's ratio of a rock mass. What about the effects of non-homogeneity, variability, anisotropy? When we excavate something, we're actually unloading. We're not loading. So there's a difference there as well. What about the degree of confinement? The in situ stresses, often they're not known. And what about confined rock mass behavior? Do the joints actually play a significant role if it's well confined? A rock mass classification takes into account the joints, but if it's very well confined, it, still got all those joints in it. So just looking at a stress strain curve, unloading, we've got one modulus. Unloading, we've got another modulus. That's under, you might say, elastic conditions before any failure occurs. But if we look at after failure or in a very jointed rock mass, you can see that after failure, the unloading can still be linear. So maybe linear analysis is still valid, but the modulus is going to be lower. Okay. Just as an example, and I can't remember where this came from, but it's in a gold mine in South Africa, and it was where the closure of the stopes was actually measured, and it was modeled using a linear analysis. And you can see that there was a difference, but the actual monitoring points could only be put in some distance behind the face. So some of the closure was actually lost. And it was modeled with maybe a modulus which was too high, because in a stratified rock mass, like the gold mining environment, the unloading modulus is going to be less than the loading modulus. But you can see that the behavior was modeled perfectly by the linear analysis. So it raises the question of whether we should take into account all these joints in a confined situation or not. Okay, I put this in, it's a three-dimensional strain stress matrix, and you can see there that there are 3 normal moduli, 3 shear moduli, so that's a total of 6 different moduli, and 3 Poisson's ratios. So in the different directions, you can have different moduli and different Poisson's ratios. So to assume from a rock mass classification that you only have one modulus and you guess a Poisson's ratio, you can be very, very wrong. Okay, so 6 moduli, 3 Poisson's ratio. The jointing in a rock mass and different extents of confinement in different conditions will always mean that the modulus and Poisson's ratio are likely to be different in different directions. Poisson's ratio to me is very important, because when you create an excavation, you create a free surface. So the stress normal to that surface is 0 at the surface. Okay, so the deformation of that surface is going to be dictated by the stresses in the other direction and by Poisson's ratio. So the strain will be extension in such cases, and it can be extension in a compressive environment. So even some distance into the rock mass, you're getting extension, and that can often lead to fracturing near surface. Okay, I think Gerry van Aswegen said that something like 80 or 90% of the fractures that you observe, in gold mine, near gold mine stoping, are extension fractures. So another alternative is the determination of rock mass properties by back analysis of previous behavior. So if you've seen what happens in the past, you can analyze that and then use that information to predict what will happen in the future. But it has similar drawbacks unless the new area is I say identical or very similar to the previous. That means in terms of orientation, location, cover, in situ stress, and so on. And I've seen a case where a very experienced numerical modeler actually did a back analysis, and all that data was then applied in what I considered a completely different environment to predict what was going to happen. So, can geophysical investigations improve the quality of geotechnical information? What about logging in boreholes? I know that, we've got the straw, and the core shows relatively little information. And I know that geophysical logging down those holes can provide a lot of additional value at much less cost than an additional borehole. What about seismic traverses in different directions? Or if you've got boreholes, perhaps between boreholes. What we want to determine is whether the modulus and Poisson's ratio in different directions are perhaps different. An indication or a quantification of the confinement in the different directions. It might give an idea of the in situ stresses if we haven't got measurements there. And I know that the seismic testing is going to provide dynamic results, but can we convert those to static as well? Even if we can get dynamic results that show there's a difference in the different directions, that in itself can be very valuable. So any other geophysical techniques that could provide good information? What about the consideration of value? Just looking at some of the discussions yesterday, and I think Steph mentioned value. Value is extremely important. And I think information from geophysical investigations could provide much greater value than their cost. Management decisions at director level, I think, are also very important in terms of value. And they often look at cost rather than value. So if you spend a little bit more money, you can actually get much better information, which is going to generate much more value in the future. Okay, so thank you for listening to that. I've just got two other slides, which actually follow from yesterday. There was a lot of talk yesterday about, the sinkholes and the dolomite and so on. And I thought that one could, in fact, perhaps use exposures to benefit. And this is a tourist location in a dolomitic area where you can see all the what could be sinkholes, okay? And one can visit this place. And it follows perhaps from what Tony said yesterday, something about stones or something about stones and forests, I think he mentioned yesterday. And at the same location, this is a tourist venue, you have this. And that is called, this whole area is called the Stone Forest. And it's in China near a city called Kunming. Rather a nice place to visit. Thanks.